Okay, let's get started. We have been talking about one kind of matrix factorization, which is PCA or SVD, and now we're going to talk about a different one called non-negative matrix factorization, or NMF. And at a high level, it's quite similar. We want to take a matrix X, and we want to write it as a product of a tall and a wide matrix with a rank of R. So R is the width of this or this. And we want to minimize RSS, just like we did with PCA. But the difference is that we want these matrices to be non-negative. So no negative entries. And so when you do this, because you're putting some constraints on W and H, it cannot do as good of a job of minimizing the RSS. So the RSS, or the approximation area, will be worse. But what you get is you get more interpretable coefficients. So when you look at the entries in these matrices, the larger the magnitude of the entries, the more important they are. Because the larger the entries, the more they contribute to X. So we'll see some pictures of this. But this is, in some applications, this is very important. With PCA, if you remember, we had these negative entries. So we had negative entries both in the eigenfaces as well as the coefficients Z that we use to scale these. So they could be positive or negative, and so it's really kind of hard to say often, what the meaning of those negative entries are in some applications. Okay, so here's sort of a visual comparison. I should have just showed you this. So in this example, we have a 1024 pixel image, and we're doing a 49 term approximation. And what's a little bit non-standard about the way these figures were generated is, and there's a typo in what I say here, is that the positive entries are white. So usually when you represent grayscale images, black is 0 and white is, let's say, 1. But actually in this experiment they did, white was 0 and black was 1. So here's PCA. So this is similar to what we have seen before. Here is the mean image. And here are all the eigenfaces. There's a total of, 48 of them in this picture. And here are the coefficients that are used to scale each one of these eigenfaces. So that when you take this eigenface times this coefficient plus this eigenface times this coefficient and so on, it puts together this approximation of this original image. And when you look at the eigenfaces, they're kind of hard to interpret. They're just positive and negative entries. On the other hand, non-negative matrix factorization builds its basis vectors like those, and then these are the coefficients that scale each of these to construct this approximation. So the approximation is of a similar quality, but when you look at the components, they're sort of more interesting. Like you can see things like eyebrow shape or the bottom of the chin, the lighting there. I think you can probably find like a nose and so on. So it's a different way to take apart a signal into building blocks and build it back up. But because all the building blocks have non-negative entries, in some applications, that's much preferable to ones where the building blocks and the coefficients can be negative. Okay, so that's the idea behind NMF. Any questions? All right. So let's just do a quick comparison of NMF versus PCA. So in NMF, we approximate X by this tall times wide matrix. PCA, we can use an SVD. So we have a tall, diagonal, and wide matrix, but then we also have the mean component there. So both of them are low-rank approximations. NMF can only be applied to a non-negative matrix X, whereas PCA can be performed on any X, or SVD can be performed on any X. Non-negative matrix factorization gives you non-negative factors, whereas PCA can have negative elements in its factors. NMF will give you non-orthogonal columns and rows, whereas PCA gives you orthogonal columns and rows. NMF encourages sparse coefficients. Let's take a look at that. By sparse, we mean that there's not many non-zero coefficients. And when you look at these, you can see how each one of these is mostly white, meaning mostly zeros in this case, and there's just a few non-zeros. Whereas PCA, you can see it has kind of a lot of, it's not nearly as sparse. Not really sparse at all. So that can also be a useful property. And now on the bad side, NMF is non-unique, while PCA has a unique solution. And there's, this NMF problem is NP hard. There's no efficient way of computing it. So the solvers can get stuck in local minima, while PCA, we know how to solve it in closed form. So those are some of the high-level differences. Any questions? Okay. So let's go back to our XGBoost experiment. And what we do is we compute coefficients using NMF instead of PCA. And here we're plotting accuracy versus number of components on a log scale. Here's the performance of XGBoost on raw features. And what's interesting is that, and PCA is in blue. So NMF happens, at least in this experiment, to work better than PCA, and it even works a little bit better than the raw features at these values of number of components. So 100 or 300 out of, I think it was like 1580 or something like that. But this improved accuracy comes at a computational cost. So now we're plotting runtime on a log scale. And if you want to use 100 NMF components, then yes, XGBoost runs relatively quickly at 100, but there is a high cost to doing an NMF. So in fact, this is about an order of magnitude 10 times more expensive than just doing XGBoost on the raw coefficients. So if you invest 10 times as much effort, you can improve the performance a tiny bit. This is just an example. This doesn't always happen this way, but just wanted to point out that NMF is a lot more expensive to compute than PCA, at least for these dimensions. All right, any questions? Okay, so, but there's other things people use NMF for. I mentioned this briefly before, the Netflix problem. So this is an important problem for online commerce. So you want to, recommend advertisements and things to people that are browsing the web, many billion-dollar industry. And collaborative filtering is a particular approach that you can use for recommender systems. And so the way that goes like this is you envision a matrix X where the ith entry, the ith row and jth column stores the rating for product I from user J. But the problem is that you only know a few coefficients in this because you've only seen how different users have rated a few products. You would like to be able to serve them other products that you think they would be interested in, but you don't know what they are. So that's the objective here, collaborative filtering. So basically you have a matrix where there's a few coefficients are known, the rest are missing, and your goal is to fill in the missing entries. Thereby, you would figure out the ratings for all products for all users, and then you could use that to decide which ads to show them or which products to recommend for them. And this problem of completing the entries in this matrix is known as matrix completion. Famous example is the Netflix contest from, I think it was around 2010. Netflix gave $1 million to the winner. And in that case, there were 18,000 movies and 480,000 users, but there was only 100 million ratings, which corresponds to about a 1% completion rate. So 99% was unknown. And so one simple way to do this is just to apply NMF to this problem. So this is the optimization problem. You want to look at RSS, between X and W times H, but you only know the values of X at a few locations. So instead of summing over all I and J, which you would do if you knew X perfectly in advance, you only sum over the known entries in X. And this is a difficult problem, but you can use, there's various decent solvers for this. They may not give you the perfect solution, but they give you a decent solution. And of course, we are now restricting those things to be positive W and H. Okay, so the winner of the Netflix contest they did something a little bit more complicated than this, but it wasn't that much more complicated than this. This actually scores pretty well on the Netflix contest, this idea. All right, so that's just another thing you can do with NMF. And we will also talk about yet another thing we can do along a similar spirit in the next unit, which we'll talk about later today. So any questions about recommender systems or matrix completion? Okay. This matrix completion shows up in a lot of different engineering problems as well. So it's kind of a neat problem. Okay. The last thing to talk about is data visualization, which is another thing that PCA is used for. So the idea is that if you have high dimensional features where the dimension D is greater than 3, or let's say greater than 3, 4, 5, 6, up to thousands or millions, it's difficult to visualize those feature vectors. But what if we did PCA to reduce the dimensionality of those xi's to these coefficients zi that were, let's say 1 or 2 dimensional, and now we can visualize them. So this is just an example where you have 3-dimensional features. It's a little bit hard to tell what's going on, even in 3 dimensions, but you do PCA to reduce them down to 2 dimensions, and all of a sudden you can very clearly see there's a sort of structure to those different features. These were labeled features, so these are the features labeled red, green, and so on. And not only are these coefficients interesting to look at, but sometimes the principal components are also insightful. So let's look at another example. We talked about MNIST, which was the data set with images. I'm trying to remember how big they were. They were I think maybe it was 19 by 19 grayscale images. And they had 10 classes. Each one was a handwritten digit between 0 and 9. And so what we've done here is we've taken, I believe that D was, I think it's 784, if I remember right. We've taken those 784 dimensional feature vectors and used PCA to get them back to 2 dimensions. And then we're plotting, and we're coloring the points with their label. So like these are all the 9s from the data set. These are the 8s. These are the 0s, the 1s, and so on. And so you can see that there is a grouping, right? You can see things are sort of grouped together, but there's also a lot of overlap. So these are the Z coefficients, the ZI, now they're 2-dimensional. And then these are the principal components. So these would be like the V1 and the V2, of course formatted in 2 dimensions. And they're interesting to look at. So you can see that the most important component is something that sort of has the information of like 0 versus 1. So this is an image where you have positive here, negative here, and zeros elsewhere. And if you look at this kind of left to right axis here, you see that the 1s are on the left side and the zeros are on the right side. And so that is kind of showing that this principal component measures like something like how much like a 0 versus like a 1 is any given digit. And then when you look at this second most important principal component, it's a little bit more complicated, but you see that there's sort of like things where you would combine this and this to get different locations here, and you can see that it's going to give you information about like whether it's a 2 versus a 7 versus a 9 and so on. And when you look, for example, up here, you see the 9s and the 7s, whereas when you look down the other direction, you see things like 2s and 3s and so on. So that's what this distinguishes in the data. Okay, so that's just a visualization of PCA on the MNIST data set to give us an example. All right, any questions? Okay, great. So, so PCA is definitely a common technique to use, but as we know, it's relatively simple. It's just this linear dimensionality reduction algorithm, and when you apply it to data sets, you get a lot of overlap. So it doesn't really work as well as you might like. You would ideally like to see if there's some kind of nonlinear dimensionality reduction that really does a better job of separating these different classes. And so there's a number of classical methods to do this, such as kernel PCA, isomap, local linear embedding. We're not going to talk about any details there. You can click on the links. But these days, what people tend to use are things like TSNE and UMAP, and maybe PACMAP. So here's just another example. This one has the dots much smaller than the previous page, but this is pretty much the same thing we saw before. A lot of overlap between the different MNIST classes. But with TSNE, you get a much better separation. And with UMAP, it's even better still. So I want to emphasize that TSNE and UMAP, they did not know, or PCA, they did not know the class labels, right? They were just given the features alone, and they were sort of asked, can you reduce them to 2 dimensions in a way that maybe tries to separate things into clusters. But what's really interesting is that when you plot those points and then you plot the class labels that those algorithms didn't know about, you find that they actually really did a good job of separating the different digits in the data set. And this kind of gives you an indication that if an algorithm like TSNE or UMAP can do this successfully, then there must be some classification algorithm that can also cleanly separate these digits, right? Because these algorithms didn't know anything about the labels. The classification algorithm has an added advantage that it also knows the labels. Even without knowing the labels, it was able to group things into non-overlapping clusters. So that's one time when you might want to use these, is if you have a data set and you're not sure whether the data set is something that's too hard to classify. And so you can give it to t-SNE or UMAP. There are some tuning parameters you have to play with, but from that you can get a sense for how overlapped are these different classes. And if they look good, then definitely there's going to be a classifier that separates them. Okay. So, all right. And we won't get into how they work, but they're very easy to use, and you can read about them more if you like. All right. Any questions? Okay, great. So that's it for this unit. And let's move ahead to Unit 11. This is going to be, I think this is the last unit I'm going to do. There is another unit that I could do on convolutional neural networks, but I kind of think maybe we've had enough. I don't know. What do you guys think? You want this to?
Have time as well.
Yeah, we might have enough time to cover it, or it would be more material for the last exam too.
Oh, we couldn't like leave that out of the exam just as a.
See, that way you guys get a break, I get a break. Yeah, I do. I can put them up.
I'd love to.
Okay.
Yeah, read through
Yeah.
it, as long as it's not an exam.
Okay.
Thank you.
Sure. Okay. So, but clustering is definitely a useful thing to know about. It's a different task than we've considered. So, in clustering, you're given a data set, just with features. There's no labels, and your objective is to partition the data set into k groups, where samples within a group are similar and samples across groups are dissimilar. So, for example, maybe you were given this two-dimensional data, and the clustering algorithm, again, did not know anything about labels, but in some sense, its job is to generate labels automatically from the data. So it decided that these were in one cluster, these were in a different cluster, these were in a different cluster, and so on. And you can see this makes a lot of sense. Like, as a human, if you were given this, you'd probably do the same thing. Just in terms of Euclidean distance, these things are all close to each other and so on. Here's a more challenging one where this is called the Two Moons data set. And you can see that, these are Euclidean distance is not really enough because these points are far in Euclidean distance, right? Farther than these points. But, we want all these to be in one cluster and these in another cluster. So any clustering algorithm has sort of an implicit or explicit notion of what it means to be similar for the purpose of clustering. And there's different trade-offs as to how they work. So we're going to talk about a few different ones in more detail, some of the more famous ones. Right, so this is an unsupervised task called clustering. That's the high level. Any questions? Okay, so probably the most famous approach to clustering is known as k-means clustering. And basically, in k-means clustering, what you do is you learn or design capital K different vectors called centroids such that you want to minimize this cost. So what is this cost? So we have a sum of our data samples. We have Euclidean distance between each sample and one of the clusters. But the thing that's a little different from what we've seen so far is that for each sample, so for each eye, you only use the distance to the nearest cluster or the nearest centroid for that sample. So the minimization is done for every I separately. Right? It's inside the sum over I. So this is the distance between xi and the closest cluster of the capital K of them. Is that pretty clear, what k-means wants to do? Okay. So that's the cost. So it ends up that this cost is it one of these NP hard things? There's no method that can efficiently solve this problem exactly, but there are some methods that can approximately solve it, and we'll talk about one of them. But if you run whatever method, you get these centroids, and then once you have the centroids, you define the kth cluster as the samples in X that are closest to those centroids. So in other words, if you're talking about the ith sample, xi, and you want to know which cluster does it belong to, you just find the closest centroid to xi, and then whatever k indexes that centroid, we'll call that the cluster label. So this cluster label is just an integer from 1 to k. Okay, so here's an example. We have the data set of these two-dimensional points. We run k-means. It provides us these 5. Well, we run k-means with 5 as the number of clusters we tell it to find. It finds those clusters. And now once those clusters are found, think about the decision region between those two. That would be like a line like this, right? So any samples on this side of that boundary are going to be closer to this versus this. And so that is what's responsible for this, this little boundary. But then imagine, over here, in this direction, this would be sort of competing with this. And so there's another boundary here that tells you which samples are equidistant between those two clusters. And that's what provides this, and so on. So finally, you get these decision regions where all the points within this region are the ones that are closest to this centroid versus those other centroids. And all the ones in here are closer to this than any of the other centroids, and so on. Yes?
So how do we know how many clusters do we need?
That's a great question. So for k-means, you actually have to tell it. So that's kind of like another hyperparameter.
Okay.
So there are some algorithms that can tell you, they have a way of estimating what k would be.
Okay.
With k-means, you could do things like start with 2, solve it, go to 3, solve it, treat it as a model order selection problem,
Okay.
where you look at like this cost as you solve it. And, now of course, like with simple model order selection, the cost will just go down as you add more clusters. So maybe you need to add another term like a regularization
Okay.
that penalizes how many clusters you have. But there's various methods that try to automatically determine what k is from the data itself.
Okay. Gotcha.
Yeah. Okay, and you might have heard of these before, but these cells or these decision regions are known as Voronoi cells. Okay, so that's like the objective of k-means. That's what it wants to do, and sort of once you have your clusters, this is how you. Once you have your centroids, this is how you cluster with them. Okay, any questions on the statement for k-means? Okay, so again, this is not a problem we can solve exactly, but there's a very famous algorithm that is used to solve it approximately called Lloyd's algorithm. And it's actually quite a simple algorithm. It just iterates 2 different steps. First step is for each k, each possible cluster k, you compute the sample mean, mu k, of the data within the kth Voronoi cell. That's the first step. Once you know those means, second step is for each k, you just reset the centroid at the sample mean. So let's take a look at this picture. So here's our data, and these are, we start with some initialization of the clusters, or sorry, the centroids. We start, some initialization. So let's say that these are our 2 centroids that we initialize. So the first step is you need to, figure out the sample mean for the Voronoi cell. So what is the Voronoi cell? That's like the set of points that are closer to the red X versus the blue X. So this would just be a line that bisects those 2 points, like here. And now we've used colors to label the points closest to this versus this. And now that we have this subset of red points, we just compute the sample mean of the red points, which would be like over here, and the sample mean of the blue points, which would be like over here. Okay, and now we start over. Given these 2 centroids, we would find their that decision boundary, which gives us these decision regions. So now we would compute the sample mean for this set of points, which is going to be over here, and the sample mean for this set of points, which is going to be over here. And we repeat once again. So then we find for those 2, we find the decision boundary. You can see that things are starting to stabilize. A few points have changed sides, have gone from blue to red. And you compute the sample means again, and then the new decision boundary. And at some point, so then one of the blue ones has changed to red, but at some point, after a finite number of iterations, things will stop changing. And then you will reach a fixed point where, because things are classified the same, or clustered the same, then the sample means will stop changing and nothing will change after that point. Okay, so is that making sense, Lloyd's algorithm? Just iterating, it's 2 steps. Compute the sample mean, set the center as a sample mean, and so on and so on. Okay, so again, this is not an optimal algorithm, so it can get stuck in a local minimum. So there's a couple different strategies which are common to try to improve this. So one strategy is just run this algorithm many times from different random initializations and compute this cost for each of those solutions, and then just choose the one which has the lowest cost. So that's one thing you can do, of course, at the expense of computation time. Another thing you can do is rather than just choose like a very generic random initialization, like Gaussian or whatever, you can carefully choose a random initialization. And the most famous way to do this is an algorithm called k-means++. It's still a suboptimal approach, but it does have some mathematical guarantees of, so there's a bit of theory behind it. And this is kind of what people use by default like in scikit-learn's k-means algorithm, they use k-means++ to initialize by default. And you can combine these strategies because this k-means++ is also random. You can generate a bunch of k-means++ initializations, solve those, and then choose the best. Okay, so that's basically Lloyd's algorithm and k-means. Any questions on that? Okay. Let's look at an example of document clustering. So let's say we have a huge collection of documents, a corpus, and we would like to organize them. Like these are sports documents, these are news stories, these are fiction, or things like that. And so this is basically a clustering problem. You can cluster them. This is an example of text mining. And for our demo, we will use these Usenet newsgroup articles. So Usenet was an online discussion forum that started in the late 1970s. and migrated to the internet. Was very active in the 1990s. And it's very convenient to use for a demo like this because the documents are pretty short. They look a lot like emails, these kind of short emails. And also there are ground truth category labels because you have all these different topics. Like here's a few, like there's I think like thousands of these, alt binaries automobiles, alt binaries automobiles car shows, blah blah blah. So you basically have you have ground truth knowledge of what people were talking about, and so you can cluster and then you can see how well you did according to the actual categories from Usenet. Okay, so there's a data set that's in scikit-learn called 20 news groups, which has data from 20 Usenet categories, these ones. And it gives you about 1,000 documents per category. And so you can see there's like a bunch of computer stuff, recreational stuff, science stuff, for sale, politics, and religion, and so on. So we're just gonna, for our demo, we're gonna load 4 categories, which is gonna give us 3,300 samples. And these are the categories we're gonna use. So there's alt atheism, comp graphics, sci space, and talk religion misc. And basically, you can kind of imagine a few of them are going to be pretty easy to differentiate, right? Like sci space, probably going to be pretty easy to differentiate from the others, computer graphics. But these two, alt atheism and talk religion misc, are going to have a lot of similar words, and so those might be harder to separate. Okay, so when you download this data set, you basically get this dataset.data object, which is a Python list of Usenet posts. Each post is a string. You have a dataset labels, which has it's an integer list of the category labels for each one of the posts. And then you have the target names, which tells you the category names. So just as an example, let's look at document number 10 in this data set. And we can find the label for that document, and we can extract the name, and that tells us, okay, this is coming from Comp Graphics, and this is the actual document. And basically, it's someone that is looking for help with a graphics card. So, just as an example, it's kind of like a short email. Okay, so that's what we're going to work with. Any questions so far? Okay, so the first thing we have to do now is we have to convert these strings to numerical vectors, feature vectors that we can somehow use for k-means or whatever other algorithm we want to apply. And so we're going to use a pretty simple approach called the bag of words model. And for the bag of words model, what you do is you have all these documents, and you make a list of all the different words that are used in all these documents, and these are often referred to as terms rather than words. You have to omit the common ones, words like the, which are not really going to help you, learn anything about documents because they're too common. Those things are called stop words. So you omit the stop words for your language, and you have these remaining terms, which are all the different terms that are used in the documents. So as a very simple example, here we have a data set with 2 documents, and each document is a sentence, and we can make a list of all the terms that are used in our documents. And then what we're going to do is we're going to represent each document as just an array of word counts. So in other words, here you can see document 1. Document 1 has used the word aid 0 times, has used the word all 0 times, used the word back 1 time, and so on. If it used the word back 2 times, there would be a 2 here, and so on. So this is how we have basically coded the document. So let's see. Is Thomas Wu here? Okay, what about Hannah Wang? And what about Sam Benjeridis? Okay. What about Alan Abdelnour? Okay. All right, what about Dan Kowalski? Yes, Kowalski? Yeah, that's you. Okay, so so what have we lost when we code our documents this way? So we've reduced each document just to like a count of words in the document.
Order.
Yeah, we've lost order. We've lost a lot of information, right? And we have we've already talked about language models, how they get very deep into the ordering of words and all the relationships. So this is like a much simpler idea. This is what people were doing, a decade or more ago. Bag of words model. So definitely not as powerful, but in some cases it's all you need. So it's a kind of important thing to know about, bag of words. So, but there's still a few kind of major challenges right now. So one challenge is that sometimes you'll have a document that's much longer than others, meaning it has a lot more words. So, when you look at the numbers in one column, they might just be much larger than another column because another column is a short document. Another issue is some terms are much more common than other terms. So, so some terms across all documents might have much, larger numbers than other terms. So these things can kind of throw you off. So we want to do something like a standardization to get around these issues. And so the most common way to improve features, they're known as TF-IDF features, and they're kind of a combination of two ideas. One is the term frequency feature, and what you do is you look for the number of occurrences of term J in document I, which would just be the number in this, that number, and then you divide by the number of terms in the document. So this is a way of normalizing for document length, right? So you're normalizing by document length. And basically what this tells you is it measures the local importance of term J to document I. Okay, this is all for document I, so it doesn't look across documents. For each document, you get a certain number that was computed just for that document, which is basically how often that term happened versus the number of terms. Okay, so that's the TF part. And then the other thing is the IDF part, which is the inverse document frequency. And this is looking across documents. So what you do is you look at the number of documents with term J divided by the number of documents. So if a term is very common, then you're going to see that it occurs over many documents, so this number will be relatively large. Otherwise, it can be relatively small. And you're looking at the negative log. So as we know, the negative is kind of like the same as inverting this. This is why it's inverse document frequency. And the log is just to kind of squash the range, because I think these numbers can span many orders of magnitude otherwise. Okay, so you have these two sort of building blocks. And finally, what you do is you just multiply them together to get the TF-IDF features. So you've tried to normalize for document size and for how rare words are across documents. And putting those two things together, these new features measure the global importance of term J to document I, considering all the documents you have. And as of 2015, these were used by 83% of text recommender systems. So it's a very, very standard approach. And I'm constructing X in this way to be consistent with how we've constructed it all semester. But if you start reading papers and books in this literature, you'll see that most people transpose the X that we're used to seeing. Okay, just a note. So they often refer to it as the term document matrix. And so, strictly speaking, they're talking about X transpose as the term document matrix, because for X transpose, you have you have terms that way, and you have documents this way. Okay. But for us, it's swapped. X is swapped. Okay, so that's these TF IDF features. Any questions? Okay. So this term document matrix, you can do a lot of different things with it. One idea is document retrieval. So here the goal is to find which documents are most associated with a given term or terms. So if you think about what happens when you use a search engine, you type in some words, this is exactly what it does. It tries to find which documents are most closely associated with those words. And so if we had this term document matrix and we wanted to do this, it's very easy. For term J, you would just extract the jth column of this matrix. And that's going to give you a vector. And you just choose the documents with the highest scores in that vector, right? So it's that's just one application of of the term document matrix. Another application would be semantic analysis, where you want to find relationships among terms. So if you extracted different columns of this matrix for, let's say, terms J and J prime, and then you did an inner product, the larger that inner product, the greater the similarity of those two terms. So if you didn't even know a language, but you just had this collection of documents, you could start to kind of piece together what different things mean, how words relate to each other. Okay. We're going to use this term document matrix for clustering. All right. Okay, so a few comments now on this matrix. So this matrix is generally going to be huge. It's going to be a D by N, XT is a D by N matrix, so N is the number of documents in our corpus, and D is the number of terms in the vocabulary. And so even in this toy demo with Usenet, we have almost 40,000 different terms. When you start thinking about Google, how many documents they know about is trillions probably, and terms, way more than this. So, so basically, just even making this matrix is, storing this matrix is impossible. So there's some important properties. It tends to be sparse because that means most elements are zero value. That's because most documents have just a small fraction of the words in the vocabulary. So when you look at each row of that matrix, it has mostly zeros and there's a few non-zeros. So rather than allocating space for the entire matrix, you save it as a sparse matrix. And when you have a sparse matrix on a computer, different languages have different ways of representing sparse matrices, but you have them in NumPy and MATLAB and so on. What it does is it says, first, there's kind of a list of all the entries with non-zeros, and then there's a table of what you find at those entries. Whereas a dense matrix, you would just allocate memory for every entry in this, whether it's zero or not. So that's the difference between sparse and dense matrices. Okay, so this document matrix tends to be sparse. It often is low rank, or approximately low rank, meaning if you did an SVD, you would find that there's a few large singular values and the rest are quite small. And also, the values are non-negative because they're counts. So because it's low rank, that means we could try tools like PCA for document clustering. And because it's non-negative, we can even do NMF because those are low rank methods. Okay, so now essentially we have 3 different techniques. We can try k-means, PCA, or NMF. Okay, any questions? All right, so how do we do this in Python? So they have this nice method, the TF-IDF vectorizer method. Super easy to use. You just instantiate it, you tell it which language the stop words come from, and then you just do fit transform on your data set, and it computes this vector x. And in our example, you can see that the number of documents is 3387 and the number of terms is 38777. Okay, now that we have this, we can just do k-means clustering or whatever clustering algorithm we want to do. So let's just take a look at some of these TF-IDF scores. So let's consider the same post that we saw, this post. Let's look at the TF-IDF scores for this post. So, okay, so remember that the TF-IDF scores is basically a score for every term that's in the vocabulary. The vocabulary is almost 40,000 long, but this document, had not many words in it, and so when you rank order the words or the terms with the highest TF-IDF scores, you get you find that these have non-zero scores, and then after this point, all other terms have 0 because they don't appear in the document. Okay, and when you look at the terms with non-zero scores, remember that it's kind of a combination of how many times those terms appear in the document, but also how rare those terms are across documents. So when you look at the highest ones, there's POV has the highest TF-IDF, and then these next 2 are tied. So this is because all these 3 terms appeared only in this document, never in any other document, because these are kind of weird things like hello but misspelled with the E to the A. This is like a very particular graphics card, it only appeared there, POV. Now, why is POV higher than the other 2? Well, if we go back to the document itself, we can see that POV actually came up twice, whereas these other very rare terms came up once. Okay, so that's kind of explaining how those TF-IDF scores are generated. Okay. And obviously, this vector is extremely sparse. There's, about maybe 25 out of 38,000 are non-zero. The rest are 0. Okay. Any questions on these scores? All right. So these scores are what's most useful for document clustering. So we can just run k-means. So here you can see we're initializing according to k-means plus. We have to tell it the number of clusters to use. We're going to tell it 4, which is, maybe we don't always have that information, but in this case, we'll pretend we do. We are only going to use one initialization rather than several, and we'll let it run a maximum of 100 iterations. So this is printing out what happens, and it actually only ran for 21 iterations, and it stopped. And this is plotting I think probably the k-means score. So let's see what happened then. So k-means, it computed 4 centroids. So what is a centroid? It's a a 38,000 length vector of TF-IDF scores, which sort of represent, one of the centers of a cluster. And so let's plot or print the 10 top scores in each centroid, or the words corresponding to those 10 top scores. So we have, let's look at centroid 3 maybe first. So in centroid 3, the 10 most important terms you can see are all things that or almost all of them seem to be associated with computer graphics. Centroid 2, space, NASA, shuttle, launch, orbit, these are closely associated with space. Centroid 1, you see some religious terms, which could come from atheism or talk religion misc. And the first one, it's hard to say what it corresponds to. Centroid 0. Okay, so this is just kind of like looking at things somewhat heuristically. Let's try to get a better idea by computing a confusion matrix, because we actually know where these posts came from. So we can compute a confusion matrix similar to what we do in classification, and we'll normalize the columns. And so this is a confusion matrix. And so here we're plotting the different clusters. And so because we're normalizing the columns, each column is now a PMF across the true categories. So when we look at cluster 3, you can see that 97% of the 7% of the documents identified in that cluster do come from computer graphics. Cluster 2, 99% come from SciSpace. So those are definitely successful clustering. Cluster 1, you can see that it is 61% from alt atheism, 39% from talk religion misc. So it's doing maybe a reasonable job because those may be very difficult to split apart. But then in cluster 0, something has gone wrong. It's just sort of uniformly allocated across the 4 ground truth clusters. So it didn't really do anything useful. Okay, so that's what we have. And then we can even take a look at a clustering error. So let's say we're looking at computer graphics, cluster this one. You might wonder, like, what happened in some of these errors? So this is an example of an alt-atheism post that was clustered as computer graphics. And when you look through it, you see that it's using many color terms like red and color, red, and so on. So it's maybe not surprising that K-means thought that this was more of a computer graphics issue, because a lot of them also talked about colors and color names. Okay. All right, any questions? Okay, so, sorry, I've gone over time. So we're almost done. Next time what we'll do is we'll look at applying low-rank factorization to this, and then we'll talk later about a completely different methods, Gaussian mixture models. I will see you guys on Friday.